Session for engineering mathematics. My name is Mithilesh. I am the masters. I have completed masters from IIT Delhi in engineering mechanics, and I will be conducting this session for you. Before we go into this demo session, just to get a feel of how much you are aware of the syllabus and how much weightage this subject has, maybe you can put some comments in this chat. Do you
Sir,
know
one
what?
thing I will add, sir, here is students are from different branches, so
Mhm.
weightage may vary
Yeah,
branch
yeah,
to
correct.
branch. Yeah,
Yeah.
please take
Uh,
care. And yeah, one more thing I will add here. CS people, we right, sir, they have very limited topics, especially
yes.
linear algebra, calculus, and PS.
Calculus.
Remaining
Yes.
branches have more syllabus, so please
Yes.
address that as well.
Yes.
Thank you.
Yes. Correct. Uh, yeah, as Dinesh sir has mentioned, CS students will have, especially from core engineering mathematics, the topics are linear algebra, calculus, and probability and statistics. However, for rest of the branches, we have multiple topics. Apart from these three topics, there is also Laplace transform, complex variables, differential equations, Fourier series, yeah, etc. Okay, and roughly for the other branches, mm, uh, aerospace, mechanical, EC, and all branches, I would say you can expect like maybe 10 to 15 um, marks, roughly from in from this subject. So it's quite important topic for all the branches, I would say. Uh, Calculus is one of the biggest topic um, in this whole subject. Uh, as I said, there are a lot of topics in calculus. We will today just focus on the calculus. I will share with you what is the syllabus in this chapter, and then we'll touch base on some specific aspects of it. Uh, so let's start the session with introduction to calculus. This is the overall syllabus for us from the basic calculus. Apart from that, for some branches we also have the vector calculus, which I'm considering it separate, not part of this basic calculus. And in this, I'll use a laser pointer. So in this, we have the topics such as limits and how limits is used to define the continuity and differentiability of the function. Then we have another topic, mean value theorems, um, which will help us to um, understand the later maxima and minima as well. And then we can see definite integral, indefinite, or you can call it as improper integrals, partial derivatives, and maxima, minima, and multiple integrals. So overall, the essence of this topic is we have in syllabus both differential calculus as well as integral calculus. Okay? And it starts with the limits, continuity, and differentiability. Maxima, minima is application part of the calculus where we will study how exactly this differentiation helps us to calculate the maxima or the maximum value or the minimum value of the function. Yeah. Today, we will touch base on the basic aspect, which is limits, continuity, and differentiability. Since this is a demo session and we have limited time, we will be focusing on the first part of it, limit, continuity, and differentiability. Feel free to put your questions or comments in chat throughout this presentation. I have connected through mobile. I can see your questions and I'll be able to address it. Okay, so with that, I will proceed to the next slide. Yes, so when we say a function is said to have limit L, we write the limit in this way, right? Limit x tends to a f of x. If a function f of x is getting the value L, if the value of x approaches a, then we call it as function f of x is said to have limit L. Okay, and mathematically we write it like this. Okay, the meaning of this limit x tends to a f of x is equal to L means the function will the function f of x will have the value of L as x approaches a. A is our point of interest. Yeah, and then yeah, we'll study later if you approach it from left hand side, right hand side, and all those details. But in general, limit x tends to a, as we approach a, what value of the function we are going to get is our point of interest. Then we study this topic, limit, continuity, and differential. Yep. So that's the basic definition. May I proceed to the next slide? Okay, let me proceed to the next slide. Another point we have is test of existence of limit. Okay, when we say limit exists, so let's consider a random function. I have drawn a certain function f of x here, and the point of interest is a. If you approach the point a from left hand side or the negative side, I would say, and or from the positive side, which is the right hand side, and what you expect, you expect that for this function you are going to get the same value of f of x, right? So limit x tends to a from the negative side or limit x tends to a from the positive side, the value of the function is giving you the same or the value of the function is same. In that case, you can say the limit exists. Yeah, so here x tends to a from negative, it means from the left hand side, and positive it means is the right hand side. So sometimes these notations are used to define how we are approaching the point of interest, whether it's from left hand side or the right hand side. And this is the concept, overall concept, and is being used to define the continuity and differentiability of the function, which we'll see in the upcoming slides. Okay, so we will have certain value of the function here, f of x. We will get certain value of the f of x as you approach a from left hand side. We will get certain value of the function if you approach a from the right hand side. Based on how these three values looks like, we will define the continuity and differentiability, and yeah, that is what we'll discuss in the next slides. Okay, anyone have any doubts so far about the right hand limit and left hand limit? Yeah, okay. Then I will proceed to the next slide, and let's start maybe with a simple example first, and then we can go into the details of continuity and differentiability. So this is a very simple question. We have limit x tends to 1 upon x, and we are supposed to test whether limit exists or not. Yes. In simple word, test whether right hand limit is equal to the left hand limit. Okay, so this is just to get you a practice of whether limit exists or not. We will try to understand this problem in both the ways. We will try to draw the diagram and we'll see how exactly the function looks like, and we will also solve it by mathematical way. Okay, so if you try to draw the diagram, it will look something like this. Okay, so this is the value of x, and you are plotting f of x. Okay, something like this you are going to get the function. So on the right hand side, the function is kind of decreasing function from the infinity value, and from the left hand side, it is approaching, it is constant, and then it is approaching the value 0. Yeah, and let's try to understand, or let's try to see through the actual mathematical calculation. So left hand limit, what we understood is limit extends to 0 from the negative side, f of x. We can also say that this is point 0, right? We can also write it as, let's say, limit h tends to 0, f of a minus h, where h is a point. So this is a 0. So let's say this is the point which is h. So this is, let's say, a, and this point will be a minus h, because this h distance is very, very small. Okay, so it's just a different way of writing it. The meaning of these two things is same, that we are talking about a point which is very, very close to 0 from left hand side. Okay, and if I say right hand limit will be limit h tends to 0, f of a plus h. Okay, that means we are talking about a point which is very, very close to 0 from the right hand side. And yeah, maybe let's quickly solve it. A is equal to 0, so limit h tends to 0, f of minus h, and it will be, yeah, solve it, limit h tends to 0. So when you put the value, what will happen? Or let's write first f of minus h, 2 raised to the power minus 1 upon h, and h tends to 0. When you put here 0, 2 raised to the power 1 upon 0 is 2 raised to the power minus infinity, which is 1 upon, okay, let me write it, 2 raised to the power minus infinity, which is 1 upon 2 raised to the power infinity, which is 1 upon infinity, which is 0. And that is what we can clearly see. As you approach 0 from the left hand side, you are approaching towards the value of the function 0. Right? That is what we can see through this diagram as well. And same thing you can do with hello, can you hear me? Yeah, okay, good. Then let's go to the next slide, and we will talk about right hand limit. Okay, please try to find the right hand limit. The right hand limit. What is the right hand limit? Is limit x tends to 0 from the positive side, f of x, which is limit x tends to 0, f of a plus h. A in this case is 0. Since a is equal to 0, we can write limit x tends to 0, f of h, which is, you can write down the function 2 raised to the power 1 upon h, which is 2 raised to the power 1 upon 0, which is 2 raised to the power infinity, and 2 raised to the power infinity is infinity. And that is what we have seen here, that as you approach 0 from the right hand side, the value of the function is going to infinity. So sometimes, if you are good at drawing the figures, you can also conclude the answer without even solving it. So this chapter, continuity and differentiability, is very important, or it's very easy, I would say, if you are habituated with the drawing the functions. Okay, and yes, this continuity and differentiability topic I will explain to you using these figures. So the answer for this is limit does not exist. Left hand limit is not equal to the right hand. Okay. Okay. You can say limit does not exist.
Sir, you, I
Anyone have
think,
any?
disconnected in mobile. Can you join in mobile and keep track of uh, chat also? So, meanwhile, guys, any doubt in this? Just like Sir has demonstrated, how we can check limit problems, or any other doubt related to mathematics also, be free to share in chat. So, we want session to be interactive, guys.
Yeah, yeah.
Please be free to. And sir, yeah, thank you, sir, for joining. Yeah, please continue, sir.
Okay. Yes, let's continue. Now let's take this topic of limits little bit broader towards continuity and differentiability. Yeah. So if I give you a function, maybe let me draw a certain function. This is x, and this is f of x. And let's take any point um, x1. Value of the function is f of x1. Just by looking into this figure, can you tell whether this is continuous or not? Is this function continuous at point x1? X1 is our point of interest. Okay. And what about the differentiability? Is it differentiable at that particular point? Yes. Yeah. Yes, I think you are right. Most of you are answering it correct. So we have a certain function just by looking into it. Okay, let's consider y is equal to x squared. Okay, um, parabolic function, and it is just by looking into it at point x where we don't have any discontinuity, so it's a continuous function. Okay, and for the differentiability, yeah, you guys are not commented, but I think only Bala has commented that yes, it is also differentiable. But sometimes continuity we can easily see and tell. But what about differentiability? That also we can easily see in the figure and tell. Okay, let me explain quickly, and then we can go to some questions. Um, when we say a function is continuous, if your left hand limit, we have just studied left hand limit, is equal to the right hand limit, and that is equal to the value of the function at that point f of a, then it's a continuous function. It's a continuous function at point A, right? However, if anything is not matching, maybe left hand limit is not equal to the right hand limit, or right hand limit is not equal to the f of A, or left hand limit is not equal to f of A. If this is not satisfied, then it's a, if not, then it's a discontinuous function. Yeah, yeah. About the continuity, when to say continuous and discontinuous. Let's take one example. I have one problem here. For example, f of x is equal to x minus 1 divided by x minus 1. Is it a continuous function? Let's say my point of interest is x is equal to 1. Okay, we have one comment from Pratik. He is not able to hear. Others, can you able to hear me? Yes, okay. Maybe Pratik, if you could try again joining the session. Now my question is, at x is equal to 1, whether this function is continuous or not. let's try to draw the figure. If I put any value of the, or if I put any value of x, how f of x is going to look like is, it looks like 1 only, except at x is equal to 1, what will happen? When you put x is equal to 1, what will happen? It will become 1 by 1 divided by 1. Correct? So it's a 0 by 0 form. Correct? So it's this function is not defined basically at that particular point. But if I approach f of x, so if I approach 1 from left hand side, let's say the value I'm talking about a very um, close to 1 means what? 0.00009, or sorry, 0.99999, something like this. Okay, minus this is very close to 1, right? 1 divided by 0.9999 minus 1. You are going to get the answer 1. Similarly, if I am talking about a point which is very close to 1 but on the positive side, 1.00001 minus 1 divided by 1.00001 minus 1, you are also going to get 1. So in this case, you have the left hand limit and right hand limit giving you the similar value, but f of y don't exist. Okay, and that's why it's though your limits are giving the similar value, left hand limit is equal to the right hand limit, but it's not equal to the you don't have the function defined at that particular point 1. Okay, so you cannot conclude about the so you cannot say it's a continuous as well as differentiable. Let me go to the give you another similar question to make this concept more robust. Yeah, I have given you one example. F of x is equal to x square. Okay, this is just the another version of it. We have f of x is equal to x square. Now this function is valid for all the values of x except x is equal to 2. Yeah, and the value of the function at x is equal to 2 is 1. Now can you tell me at x is equal to 2 whether the function is continuous or not? Yeah, so now my point of interest is x is equal to 2. We have seen the figure just now. Let me draw it once again. Okay, so the function will look something like this. This is the origin. This is x. This is f of x. F of x is equal to x square. However, at particular point, here I would say I'll just here you don't have the value of the function, and in place of that, value of the function is here. Okay, x is equal to 2. So the graph is a parabola, right? But everywhere except the point x is equal to 2. This could be an imaginary, means I'm considering a random function like this. So there could be some situations why I'm giving this kind of examples is it's not always a continuous function if your right hand limit is equal to the left hand limit. Okay, so you should be also focusing on what is the value of the function at that particular point. So in this case, if I calculate left hand limit, which is limit x tends to 2 from left hand side, f of x, which is what? Take any point which is 1.99999 square, which is approximately equal to 4, right? Similarly, right hand limit, which is limit x tends to 2 from positive side f of x is equal to 2.000001 whatever whole square is again approximately equal to 4. So as you go closer and closer to 2, so you can further go closer, and you can see your values are matching or approaching towards the 4, right? However, f of 2 is not 4, f of 2 is 1. They have given the question itself, right? So this is how our function looks like. Hence, you can say that this function is not continuous at point x is equal to 2. Maybe if you consider any other point, let's say x is equal to -1, x is equal to 0, 1, 3. At those points, it is continuous, no problem about it. However, our point of interest is x is equal to 2, where our left hand limit is equal to the right hand limit, but the value of the function at that point is not matching with it. Hence, it is discontinuous function at point 2. Anyone have any doubt in this? Is it clear now? Why this additional requirement is being added to define the continuity? Okay, good. Now, let's talk about the differentiability aspect. Yeah, let's talk about the differentiability aspect. What is differentiation basically? What is differentiation? Yeah, what is the practical way of, or let's say physical way of understanding the differentiation? Or in terms of, let's say, figure, if you have a function, if you take a differentiation of that function, what does this indicate? If I have f of x and I calculate a dash of x, what does this mean? And let's say my point of interest is, let's say, a. So f dash of a means what? Yes, correct, Bala. It's we are talking about the slope. It indicates the slope. Okay, it means what if you draw a tangent at that particular point, it is going to give you certain slope. Right now, when we say a function is differentiable at one particular point, so you now understood the basic of differentiation. Differentiation means the slope. If you are going to get a unique value of slope at that particular point, then we can say that the function is differentiable at that point. Okay, so requirement is you'll have a unique slope. Okay, what is meaning of the unique slope? The meaning of unique slope is your left hand left hand derivative. Now it's not a limit. If you take a derivative of the function at point which is very very close to the point of your interest, that is your left hand derivative, is equal to the right hand derivative. What is right hand derivative? Right hand derivative is the differentiation of the function at a point which is very very close to the point of interest from the right hand side. Yeah, and if that is equal to f dash of a, if this requirement is satisfied, then we say that function is differentiable at that particular point. Okay, and mathematically, you have to calculate this left hand derivative, right hand derivative, a dash of a, match all these three numbers, and if they are same, then you can say function is differentiable. Now, can you tell me how physically you can tell it just by looking into the figure? I have given you hint now. What is the let's say complete requirement of differentiability? Now, can you tell me if I give you the diagram, how can you tell whether it's differentiable or not? Yeah, maybe I'll give you a few more seconds to answer. Yes, some students are typing. Let's see the comments. Okay, Bala is saying draw tangent line based on the slope. Rohit, any other comment? Divide dx. Hmm, okay. Hmm. Any other comment? Now let me give you one simple example, and we will understand through that example. Okay. I haven't got the perfect answer so far. You guys are very close to it. Hmm. But let's try to solve this question, and then I think after this question, the concept will be clear to all of you. The new example is f of x is equal to mod of x. Can you draw this function first of all? Okay, I'll give you a minute of time so that you can type your comments. If yeah, I can see few students are typing the comments. Please draw this figure. Yeah, this is how the function will look like, right? This is x. This is f of x. My point of interest is that x is equal to 0. Can you tell me whether the function is continuous or not at x is equal to 0? Yes, continuous. Good. So yeah, just by looking at the figure, we can tell there is no discontinuity at point 0, so it's a continuous. Okay. Even you can solve left hand limit is limit extends to 0 from left hand side mod of x, and you can clearly see it put any point which is let's say mod of minus maybe 0.000001. It's almost equal to 0, right? Similarly, I'm directly writing here. You can also solve it in the detail and write your answer. Right hand limit is limit extends to 0 from positive side, and this is also you are going to get 0, and f of 0 is also mod of 0 is 0, correct? So all these things are same, hence it is continuous. What about the differentiability? Whether this function is differentiable at point 0? I just told you um, that you are supposed to calculate left hand limit, right hand limit, and the value of the left hand derivative, right hand derivative, and the derivative at that particular point. And if all these three things are matching, then it's a differentiable function. Yeah, I can see some answers are no. Anyone have any other answer? Or do you agree with no? Now, can you specify that why it is no? Why it's not a differentiable function? Constant slope in the figure. No, it's not the correct reason, Rohit. Anyone have any other comments? Yeah, feel free to make use of this chat and put your Comments? Slope is not zero at this particular point. Slope is not zero. I would say slightly beyond that. Can you think of? But yeah, you're very close to it. You're right. There is a comment from Bala and Vignesh that function is not differentiable, and it's right. Left hand derivative is not equal to right hand derivative. Correct. What is left hand derivative if you calculate? What is the value of left hand derivative? -1. Correct. Because slope of this function on the left hand side is -1. And what is the right hand derivative? Is equal to 1. Correct. And if you calculate, so it's basically not same. So that's why it is not a differentiable function. You're right. But physically, how can you understand it in a better way is at this particular point, oh, which is our point of interest, you don't have a unique slope, right? What does it mean? Left hand derivative is not equal to right hand derivatives. You don't have any unique slope. You can draw multiple tangents at that particular point, right? And hence you can say it's a non-differentiable function. Another physical way of understanding it is creating a sharp corner whenever you have a function with let's say a smooth function. Let me again draw a parabola. Okay, and if I consider any point on this, you will get a unique tangent. However, if you have a function which is maybe a sharp corner, something like this, okay, it is creating a sharp corner at that particular point. Basically, a function can be anything like this, or yeah, let's say like this. It is creating a sharp corner here, right? So whenever you see this sharp corner, it means that you cannot have a unique slope or unique tangent at that point, and that is what was our main assumption. The requirement for a differentiation is having a unique slope. That right hand derivative is equal to the left hand derivative is equal to the value of the derivative at that particular point, and that is been clear. If function is smooth, then that requirements gets satisfied. However, if function is not smooth, making some sharp corners like this, it is not satisfying that requirement, and hence you can conclude about the differentiability of the function just by looking into the figure. Anyone have any doubts so far? Yes, correct, Vala. It means if you have a sharp corner, then it means there is multiple tangents you can draw. You don't have a unique slope for it. So the main intention of explaining this through figures is you should try to draw the figure, and in that way you can save a lot of time if you can just draw the figure at and solve some questions. Maybe after some few questions you will be able to solve question just by drawing the figure without even calculating right hand limit, left hand limit, the right hand derivative, left hand derivative, and so on. Okay. Yes. Yeah. Correct, Rohit. We are always talking about the point of interest in all the question. We are writing a point, and our discussion is about that particular point. Okay. So this point in this question we were talking about point 2. If I go here we are talking about the point 1. Okay. So all the questions we are talking about one particular point. Yeah. And here the point of interest was x is equal to 0. If I consider any other point x is equal to 2, for example, whether the function is continuous at x is equal to 2? Yes, x is equal to 2 somewhere here. And whether the function is differentiable at x is equal to 2? At x is equal to 2, whether this function is differentiable? Yes, it is differentiable, correct. So what is the takeaway from this then? So we have understood this mod function is 0. Mod function is not continuous. Mod of x is not, sorry, mod of x is continuous everywhere, right? And it is not differentiable at point 0. It is differentiable everywhere. So the key takeaway from this question is mod functions are continuous everywhere. Write down. Mod functions are continuous everywhere. And another comment is mod functions are differentiable everywhere except everywhere except the point at which it becomes 0, correct. At the point at which the value of the function is 0, the mod function is not differentiable, but apart from that, at all other points it is differentiable. Are you following this? Okay, let's go to the next slide. And based on that, this is a very simple question. Based on that, I have an example. F of x is equal to mod of x plus mod of x plus 1 plus mod of x plus 2. Tell me, this function is differentiable at which point? I'll repeat the question. We have a question, and mod of x plus 1 plus mod of x plus 2. And the question is, out of this below 4 options, 0, 1, minus 1, and minus 2, at which point function is differentiable? Yes, correct, Ronak. Function is differentiable at point x is equal to 1. Why? Because at x is equal to 0, mod of x is not differentiable, right? Because at this particular, what is our learning? Learning was mod functions are differentiable everywhere except the point at which it becomes 0, right? And in this case, mod function at x is equal to 0, mod x becomes 0. At x is equal to minus 1, mod of x plus 1 is not differentiable. And at x is equal to minus 2, mod of x plus 2 is not differentiable, right? And that is why 1 is the only option. In order to be, this complete function has to be differentiable. It has, all 3 parts has to be differentiable, right? And then to achieve that, the only requirement we should satisfy is the point should not be 0, minus 1, and minus 2. Okay. Anyone have any doubt in this? Clear to all of you? So now we understood what is the meaning of limit, how limit is being used to define the continuity and differentiability, right? Sometimes left hand limit and right hand limit matches, but there is the importance of calculating the value of the function at that point, which also makes sense. So it is very easy to find the value of the limit, right? If I give you a certain function and limit extends to 0, certain function, put the value of, let's say, extends, put the value of x equal to 0 and you can solve it, right? However, let me explain. Limit extends to 0 or a f of x. What it will say? The answer is f of a. That's all. You will put x is equal to a and you'll write the answer. But not all the problems are so simple, right? And that is where, yeah, okay, I have one question, I guess. Let's look into this first and then we'll jump into the um, details of the limit. Okay, this we will not solve completely. We will draw this function and you tell me whether it is continuous and differentiable or not. Okay, so let me quickly draw this figure. Okay, I have some space here. Let me utilize it. I think I need to draw it like this. The value of the function at x is equal to 0 is 0. The value of the function for all the values of x greater than 0 is third order parabola. So it means something like this. Okay. And what about the function for all the values of x less than 0? It is sine x. Yeah, it is like this. So it is like this. X and f of x. Now look into this function, and I'll not draw the completely. It'll go like this. Is it a continuous function? Is it a continuous function? Yes, because the value of the function is approaching 0 whether you go from the left hand side or whether you go from the right hand side. Okay, so I would say left hand limit is equal to right hand limit is equal to f of 0 is 0. You are going to get it. Everything is same, so it's a continuous. What about differentiability? Is it a differentiable function? Yes, Gautam, you are right. It's a continuous. However, it's not a differentiable. Why it is not differentiable? Because you can clearly see the curve is not smooth at x is equal to 0. At x is equal to 0, curve is not smooth, right? And that you can also check by calculating the value of left hand derivative, right hand derivative, yeah, um, for this function. Okay, so the left hand derivative, look at the function. It's left hand derivative is, yeah, I think you are going to get, I think should be 1. And the parabolic curves is like it's approaching 0 like this, right? Generally parabola, the slope towards 0 is, slope towards the point is 0. A right hand derivative, I think you should end up with the 0 value. Okay, um, okay, so in simple words, your right hand derivative and left hand derivatives are will not match, and that's why this function is not differentiable, which you can directly see the figure and tell that my curve is not smooth at point x equal to 0, so it's not differentiable. Okay, you can also yeah, it's creating a sharp end, right, Rohit? You can also try to solve it and by calculating the left hand derivative and right hand derivative values. Yeah, and because f of 0 is 0, f of 0 is 0, right? F dash of 0 is also 0. So the derivative at that particular point is 0, but left hand derivative value is non-zero. And that is what is creating the difference here. So all these three requirements are not satisfying, hence this function is not differentiable. Okay. Okay, I'll repeat, Bala. To conclude the differentiability, three things has to be calculated: left hand derivative, right hand derivative, and the derivative of the function at that point. In this case, you are going to get right hand derivative and the derivative of the function at that point same, which is 0, but your left hand derivative is non-zero, because look at the curve, Bala. Let me draw a bigger picture so you can understand. So this parabola is like this and curve is like this. So this slope is non-zero, right? Well, if you draw a tangent at this particular point, it is non-zero. However, if you draw a slope at here, it is 0. So this is where it is making difference. It is creating a sharp corner here. Okay. So yeah. So in this continuity and differentiability topic, the main aim is to solve the limit, because whether you want to check the differentiability check or continuity check, you have to solve the limit. And not all the limits are easier to solve. And these are the special cases when we solve the limits. And we call them as the indeterminate forms, right? We have seen, let's say if I give a simple example, limit x tends to 0, sine 0 by sine x by x. If I just say sine x, it's very easy. Sine 0 is 0, right? But if I write sine x by x, what you are going to get is 0 by 0, which is not defined, right? It's an indeterminate form. Then in such situation, how can we solve the limit? Yeah, and that is what we are going to quickly learn in this slide. So these are the indeterminate forms. We have 0 by 0, infinity by infinity. These two types of problems we can solve by L'Hospital rule. Okay, and what this rule says is you differentiate numerator and denominator separately and solve the problem. Okay, so until you get rid of this indeterminate form. So the same problem, f of x is equal to sine x by x. It is 0 by 0, but when I put limit x tends to 0, f of x by x, applying L'Hospital rule will be limit x tends to 0, limit x tends to 0, cos x by 1, right? Cos x by 1. Yeah, limit x tends to 0, cos x by 1. And the answer is 1. Because put the value of x equal to 0, cos 0 is 1. Right? Cos x by 1, which is cos 0 is 1. Correct? Similarly, if it is an infinity by infinity problem, you apply the same approach. What you are going to get, or what you are going to do, and maybe one example for this is limit x tends to 0. Let me write it log of sin x by log x. Same problem, just by log. When you put 0, log 0 is infinity, right? So infinity by infinity form. And this problem also you can solve by an hospital rule, which says limit x tends to 0. Differentiation of log of sin x is 1 upon sin x, and differentiation of sin x is cos x. So cos x by sin x, and differentiation of log x is 1 upon x. And now you can solve this problem. And yeah, I think you are going to get x cos x, limit x tends to 0, x cos x by sin x. And you can, now if you put 0, it is converted to 0 by 0 form, right? So you can again apply the L'Hospital rule and solve it. Limit x tends to 0, cos x minus x sin x divided by sin x. And now if you put the value 0, you are going to get 1. So in simple words, if you are getting 0 by 0 form or infinity by infinity form, when you put a value of x is equal to a in the function, the way to solve this is L'Hospital rule, which is differentiating numerator and denominator and then putting the value of the a. What to do in this third form? Anyone? If it is 0 multiplied by infinity form, how can we solve? Yeah. How can we solve? Yes, you are right. So it's like a convert this form into 0 by 0 or infinity by infinity by rearranging the terms. Rearranging. So if it is 0, 0 means you can write it as 1 upon infinity, right? Or if it is infinity, you can write it as 1 upon 0. So in simple words, 0 cross infinity can be converted to infinity by infinity or 0 by 0. Let me give an example quickly. Limit x tends to 0, x log x. So if I put 0, it is 0 into infinity form. So what I'm going to do is just rearrange the terms. Limit x tends to 0, log x divided by 1 upon x. Now it is converted to infinity by infinity form, and you know how to solve it, right? You can solve it by using L'Hospital rule. Yeah. So this is about the third type. Now, can you tell me about the fourth type? Okay, I can give some example about it. It is infinity minus infinity form. How to solve the infinity minus infinity form? Anyone? Anyone? So it's a taking LCM. Yeah, taking LCM. If you take the LCM, you can solve it, right? And let me give a quick example. Limit x tends to 0, 1 upon x minus 1 upon sine of x. It is, you can clearly see it's infinity minus infinity form, but after you take the LCM, limit x tends to 0, sine x minus x divided by x sine x. It is now 0 by 0 form, right? So by taking the LCM, you can convert this form into 0 by 0 or infinity by infinity, and then you can apply the Hospital rule. You know how to solve it. Yeah. And what about the last type? If it is 0 raised to the power 0, infinity raised to the power 0, or 1 raised to the power infinity, take log, correct? Right. Take log and solve. So if I have a question like limit x tends to 0, x raised to the power x, so it is 0 raised to the power 0, I will consider this as a y, right? And take log on both the sides. Log y is equal to limit x tends to 0, log of x log of x, which can also be written as log of x by x, right? And now it is infinity by infinity. So you can write x log x, but it is what? 0 into infinity form. So you know how to do handle this, which is rearranging the terms. Log x by 1 upon x. And now it is infinity by infinity form, and you can apply the Hospital rule and solve it. But remember, you always get the value of log of y. Maybe in this case, you will solve and get 0. 0 is not the final answer. Y is equal to e to the power 0, which means 1. Okay. Always remember to take the exponential value of this answer, because you are calculating log of y, not y. Okay. So these are some special cases which are also important when you solve the limits problem. These are the only critical cases. Otherwise, you will be able to directly put the value of a, and you'll be able to solve that limit. Okay, so that's all I have for today. Anyone have any doubt? Whatever we have studied today, is that clear to all of you? We started with the limits, understood how limit exists, continued that approach to find the continuity and differentiability, trying to relate it with the figures and understand physical sense of continuity and differentiability. We put a special emphasis on the mod functions, and then we discussed about some special cases about the limits. So that's all from my side. Thank you all for joining this session. Okay. Yes, and I encourage you all to follow us. And yeah, thank you all.
Yeah, thank you, sir. Thank you, guys. So, how was class, guys? Any concern, any doubt, any query?